In order to get anywhere with our math, we need a way to represent not just points in space, but also vectors. So first of all, what are vectors? There's a couple of perspectives on this. First, we could say that a vector is a quantity that has both a magnitude and a direction. Another point of view is that vectors are relative quantities, or quantities representing a change. And these should be contrasted with points, which are absolute quantities. So, for instance, if we have 2 points in the plane, call them A and B, we can depict the displacement in going from A to B by drawing an arrow from A to B. So this directed line segment with initial point A and terminal point B represents a vector that we denote AB with a line over top of it. The reason I say represents a vector rather than is a vector is if we have 2 other points, C and D, we'll say that the vector from C to D is equal to the vector from A to B if these line segments differ by a translation. In other words, 2 vectors are considered equal if they have the same magnitude and the same direction. The initial point isn't part of the data of a vector, but it's just how we draw it. Now, that being said, once we choose an origin, there's a way to go back and forth between points and vectors. Namely, there's exactly one directed line segment representing this vector that starts at the origin. And so we associate this vector with the endpoint of that line segment and vice versa. So now suppose that in addition to picking an origin, we've set up a 2D coordinate system centered at this origin. Now we can describe that endpoint using a pair of numbers, its x and y coordinates. And we'll describe the vector using those same numbers, but using angle brackets to emphasize that it's a vector, not a point. So let me write this down. We'll say a vector is in standard position if it's drawn with its initial point at the origin. And really I mean that the arrow that we draw to represent the vector, again, the vector itself technically doesn't have a starting point. So then if V is in standard position, we take the coordinates of its terminal point in our coordinate system and write those down and call this the component form of V. And I did this in 2 dimensions, but we can do exactly the same thing in 3 dimensions. One thing this component form is useful for is lengths. So if the component form of V is V1, V2, V3, then by the formula, the Pythagorean theorem that we've already worked out in 3 dimensions, the length of this vector will be square root of V1 squared plus V2 squared plus V3 squared. So the sum of the squares of its components and then square root that. So for example, let's say we were asked, find the component form and length of the vector that starts at the point -1, 2, 3 and ends at the point 0, 1, 1. So to find the component form, we'll subtract the coordinates of the initial point from the coordinates of the final point. So 0 minus 1, 1 minus 2, 1 minus 3, and that'll give us 1, -1, -2 for the component form. So that's our answer for A. Component form is 1, -1, -2. Now for B, we apply this formula to get the length is square root of 1 squared plus -1 squared plus -2 squared is square root of 6. So in summary, we can think of points as providing an answer to the question where, and vectors as answering the question which way. In these lectures, I'll write points using parentheses and vectors using angle brackets. Be warned, this is not a universal convention. It is what the textbook uses, but if you look at other books or on the internet, they might not stick to this convention. So just be aware of that. Anyway, in using variable names for vectors, we often denote them either in boldface like this, or if you're writing by hand, by drawing an arrow over top of it. And these notations are standard. The main example of a point quantity for us is going to be position, whereas displacement, velocity, and acceleration are all vectors. Some other examples of point quantities are temperature and time, where the corresponding vector quantities are change in temperature or change in time. So like 12:30 p.m. is an example of an absolute time, whereas if you say one event is an hour earlier or an hour later than some other event, that's a relative time or a time vector. So let's go through an example to see what am I talking about. So let's say we're given some word problem that's like Alice is standing 50 meters away from a building that's 10 meters tall. Bob, from the top of the building, throws a ball toward Alice with a horizontal speed of 20 meters per second. And maybe we're assuming Bob to have height 0 or whatever, so he throws it exactly from the top of the building. And then it could ask us something like how far the ball travels or how long it takes to hit the ground. But whatever this problem happens to be, let's say one person goes about solving this by setting up a coordinate system centered at Alice with axes like this. So up and right are positive. Then their expression for the acceleration vector of the ball will be 0, negative 9.81. And let me write a subscript A here to emphasize that this is in that coordinate system. Then their velocity vector will be negative 20 and negative 9.81 t, where t is the time since the ball was thrown. And then their expression for the position, now this is going to be a point, will be 50 minus 20t, comma 10 minus 9.81 t squared over 2. Okay, now let's say someone else is approaching this problem, and they set up their coordinate system to be centered at Bob with axes like this. So now right and down are positive. And maybe they're also measuring in feet rather than in meters. So this person's expression for the acceleration vector is going to be 0, 32.17. And again, I'll put a B to emphasize that it's in this coordinate system. Their expression for the velocity of the ball will be 65.6, 32.17 t, and then their expression for the position of the ball will be 65.6 t and 32.17 t squared over 2. And so the point I want to make is that the formulas for converting between these two coordinate systems are different depending on whether we're talking about points or vectors. So to convert a vector in the A coordinate system to the B coordinate system, we multiply the X and Y coordinates by negative 3.28. So 3.28 is meters to feet, and then the negatives are just because the directions of the axes are different. But to convert a point, the formulas will be negative 3.28, now x minus 50, and negative 3.28, y minus 10. So if we're converting vectors between coordinate systems, we just have to scale the entries. But to convert points, we also have to offset the origin.